this is Ryan Lewis, and I'd like to welcome you to the Hydroelectric Footwear Team video presentation. In the next hour, you will hear from many members of our team who will share with you all the work we've done, which has allowed us to take a basic idea and see it grow into something realizable. Now, I'd like to introduce you to Krista, who will talk about our project in greater detail and also one vision of the world in 2030.
Hello, my name is Krista Van Sciver, and today I will be discussing the project description, the project background, our project planning methods, task allocation, and one view of the world of 2030. In 2001, Robert Camaretta of Ontario, Canada, developed and patented a concept which has the potential to change the way individuals power their personal electronics. His idea is to take small hydroelectric generators and utilize them in shoes to generate power. As the wearer of the shoe walks, the fluid contained within the generator in the shoe will be forced through a turbine to generate power. This power can potentially be used to charge or power personal devices such as mobile phones, MP3 players, and small computers. The purpose of this group project is to take Camaretta's patent from the idea stage to a breakthrough innovation using an augmented version of the Paul and Bites design method. The project charter is to develop highly profitable hydroelectric footwear for the U.S. market. A secondary but not less important project objective is for the project team to self-organize into a learning organization. According to Singhi, real learning gets to the heart of what it means to be human. Through learning, we recreate ourselves. The 5 basic disciplines or component technologies that Peter Singhi identifies as critical to learning organizations are shown on this slide. They include systems thinking, personal mastery, mental models, building shared vision, and team learning. Throughout the whole process, the group's A0 core competencies and learning objectives were kept in mind, as these are crucial for attaining personal value out of the entire experience. This list includes the generalized core competencies and learning objectives that the group was working toward. Now for a bit of background. As we've noted before, we are using Camaretta's 2001 patent as the basis for our design. There are 5 key elements in the patent. The system will use an electrically non-conductive fluid, in our case water. Sacks to hold the fluid are placed in the heel and the toe section of the shoe. Conduits connect each sack to a microgenerator. As water moves back and forth in the sole, it moves the blades of a tiny turbine. The microgenerator is located between the 2 fluid-filled sacks and includes a vane rotor which drives a shaft and turns the generator. The image on the right is from the original patent and illustrates these components. Now, as a person walks, the compression of the fluid in the sac located in the shoe's heel will force fluid through the conduit and into the hydroelectric generator module. As the person continues to walk, the heel will be lifted and downward pressure will be exerted on the sac under the ball of the person's foot. The movement of the fluid will rotate the rotor and shaft to produce electricity. An exterior socket will be provided to connect wires to a portable device. A power control output unit may also be provided to be worn on the user's belt. Electronic devices can then be attached to this power control output unit, which will provide a steady supply of electricity. Our project planning and overall project coordination and collaboration was accomplished primarily through Wigio. Wigio features we used for the project included virtual team meetings, conference calls, file sharing and editing, real-time polls, and group emailing. The task allocation for our project was done over Wigio conference calls. At the beginning of the project, several virtual meet-and-greet sessions were scheduled where team members had an opportunity to introduce themselves and learn about other team members. There were several polls submitted to determine what our team breakdown should be, and for people to indicate their interest in working on specific teams. An organization and scheduling team was established, and a project kickoff meeting was held on March 13th. The primary method we used for planning was to 1. Divide the 30-person group into sub-teams and determine co-leads based on user input. 2. Lay out an initial Gantt chart of generic Paul and Bites tasks. 3. obtain a to-do list from each co-lead that was relevant to the original plan and rely on their ability to manage at the sub-team level. And 4, provide reminders to and obtain status updates from each team. The O&S team discussed several methods and tools for project management, and we decided we would use Microsoft Project for schedule management since we had access to the tool and were both familiar with its use. Due to the significant inter-team dependencies, we also decided to use a dependency list to manage our dependencies. The O&S team worked with each team's co-leads to develop their schedule of tasks, identify dependencies, and determine deliverable status. Weekly project rhythm meetings were established where the team co-leads discussed current and upcoming work, any challenges, issues, and risks. Strategies to mitigate risks were discussed and agreed to. Action items and tasks were assigned based on desire, capability, and necessity. Attempts were made to balance the workload across all team members. The project schedule was structured based on the Paul and Bites design method. The high-level sections are shown here. Our schedule had approximately 100 summary and detailed tasks, and we estimated 945 total project hours based on 5 hours per week per engineer. Within each of the high-level categories, project teams identified specific deliverables, tasks, timelines for completion, and resource assignments. The schedule was updated weekly with input received from the team co-leads. One of the topics of discussion during the team kickoff meeting was how to track individual work and effort. The project members agreed that team members would track contribution hours within the team, evaluate physical work submitted by other team members, and submit a peer review at the end of the project. Co-leads agreed that they would record meeting attendance. Personal tracking was done at the individual level, while team progress tracking was done by the O&S team. Responsibility of team management was split among the O&S team members. Each project team member researched trends and predictions for manufacturing in the future and developed his or her unique vision of the world of 2030. This slide represents one such vision. As we begin our research, models for the future of manufacturing are driven by the challenges facing the manufacturing industry today, such as forecast of changing market conditions, global policies on energy and environmental protection, and anticipation of advances in technology. 3 potential manufacturing models for the world of 2030 are lights-out manufacturing, traditional manufacturing, and microfactories, virtual factories, and democratized industry. Lights-out manufacturing is a manufacturing methodology rather than a specific process. Factories that run lights out, and often without heating or air conditioning, are fully automated and require no human presence on site. For traditional manufacturing, there's a lot of economic pressure on traditional manufacturers to become more flexible, more agile, and to control cost. Standardization combined with additive manufacturing and rapid prototyping is one combination of processes and technologies that will help traditional manufacturers become more flexible and agile. There's also renewed interest in manufacturers becoming leaner and greener. For microfactories, virtual factories, and democratized industry, Chris Anderson of Wired Magazine describes the future of manufacturing as the next industrial revolution, a future where individuals and small groups can use open-source, custom-fabricated, do-it-yourself product design to bring their ideas to market. Anderson bases his theory on the idea that the tools of factory production, from electronics assembly to 3D printing, are now available to individuals in batches as small as a single unit.
Hello everyone, Mongwi To here, and I'll be discussing mass collaboration with respect to our project. We were open in that our ideas were shared among the group, rather than being closed off to only certain employees, like in a traditional firm. We thought only like producers, but also as consumers, coming up with ideas that, it's our typical consumers would want on a project. In addition, we use shared software and resources that will be discussed later, instead of in-house software that typically traditional firms keep hidden. The playing field here was leveled in that any individual, no matter what their background was, could work on the project. So why did we use this concept? And the reason is that we're moving to a fast-paced world, globalization 3.0, as Friedman likes to call it, where typical or traditional firms can no longer depend on using only internal capabilities. So what tools did we use in order to collaborate as individuals? We used Wizio, which was a free online software that allowed us to exchange ideas via chat forums. And we can exchange ideas as a group or within subgroups if necessary. We were able to hold meetings via conference numbers and of sharing screens, as well as polling to make decisions, especially towards the beginning when we were trying to iron out the deliverables. Basically, we were able to exchange ideas very rapidly and continuously throughout the project using this tool. We had many different backgrounds, so we were able to come up with varying ideas and opinions. Although we had only mechanical engineers, we had mechanical engineers working on every aspect of the project. So this shows that no matter what your background is, in this type of environment you can take on any role. And it can be very effective. For instance, in the user input phase of the project, we were able to not only think as producers, but also as consumers to come up with the final deliverables of the project. So what did we do to maximize the mass collaboration effort? What did we do to continually motivate each of the members? As we discussed earlier, we're in a fast-paced environment where technology is continually changing. And so you're going to be taking on various roles no matter your background, and that's how we aligned ourselves. In our group, everyone took on at least 2 different roles, so you were able to learn, if not from one role, then from one of the other roles, and how you can improve and how you can work more efficiently in the group. In addition, because anybody can work on any role and work on any part of the project, everyone has the capability or has the power to decide, what they work on. And because of this, because you have the power to choose, you're able to stay motivated throughout, since you're able to decide, at what time you want to put in the most effort and what parts of the project mean the most to you. In addition, you're working with individuals from many different locations, mostly from the U.S., but also a handful from different parts of the globe. So you're able to learn from different individuals, and through this learning experience you're able to stay motivated and continue to want to grow and continue to want to build on the project. So this ends my part of the presentation and how we use math